Welcome back. So, we've talked a lot about agents and environments and getting rewards. But how does a machine actually learn from its mistakes? What's going on under the hood? Today, we're going to pull back that curtain and look at the surprisingly elegant math that really powers reinforcement learning. Okay, let's just dive right in.
It really all boils down to this one question. And here's the spoiler, it's not magic. It's actually a beautifully structured, logical process of just updating what you believe based on what you experience. And that's what we're going to do. We're going to break down exactly how that works step by step.
So here's our game plan. First, we'll lay out the game board, the rules of the world. Then we'll figure out how to decide if an action is good or not. After that, we'll see how the agent learns from just one single experience. And finally, we'll put it all to the test with a real-world traffic light example. Sound good? Let's get started. Okay, first things first. Before an agent can learn anything, it needs a world to play in, right? In reinforcement learning, we define that world with a specific mathematical framework. You can think of it as the official rulebook, or as we're calling it, the game board for our agent. And that framework has a name. It's called a Markov decision process, or MDP for short. It's just a formal way of describing the environment. What choices the agent has, what might happen next, and what the rewards look like. Honestly, this is the bedrock for everything else we're about to talk about. So, an MDP breaks the entire universe down into just 5 key parts. S is the set of all possible states, basically any situation the agent could find itself in. A is the set of actions it can take. P is the probability, the odds of what happens next if you take a certain action. R is the immediate reward, the points you score. And finally, there's gamma, the discount factor. This one's important. It basically decides if the agent is a live-for-the-moment type or if it's planning for the long haul. Now, the secret ingredient that makes all of this work so well is something called the Markov property. It's a really simple but super powerful idea. The future only depends on where you are right now, in the present. The past doesn't matter. Everything the agent needs to make the best possible choice is baked into its current state. And that simplification, that memorylessness, is what makes learning manageable in the first place. Okay, so we've got the rules of the game, but how does an agent actually decide what to do? It needs some way to figure out which actions are good and which are bad, not just for now, but for the long run. And that brings us to this idea of value. This is where something called the Q function comes into play. You should think of it as the agent's crystal ball. For any state it's in, and for any action it could possibly take, the Q function, written as QSA, spits out a score. That score is a prediction of the total reward it's going to get from that point on. So it's pretty simple. The higher the Q value, the better the action. So how do we figure out that Q value? Well, we use a clever little thing called the Bellman equation. And the logic behind it is actually super intuitive. It just says that the value of doing something right now is the reward you get immediately, plus the value of the absolute best move you can make next. That's it. It's this simple recursive loop of what's good now plus what's best next. Now, the Bellman equation tells us what the perfect value should be. But in the real world, an agent starts with no idea. It has to learn this value from experience. And it does that through a process called Q-learning, which basically updates its knowledge one tiny step at a time. I think the best way to think about the Q-learning update rule is to see it as a simple course correction, right? The agent starts with a guess about an action's value. That's its old knowledge. Then it takes the action, sees what happens, and it just nudges that old guess a little bit closer to the new reality it just saw. And here's the anatomy of that nudge. Alpha here is the learning rate. It just controls how big of a step we take with this new information. Then we have R, the actual reward we just got. And we add to that our best guess of what the future looks like from our new state, S prime. It's this beautiful mix of what just happened in reality and what we predict for the future that really drives the learning forward. All right, that's enough theory. Let's make this real. We're going to apply this exact same update rule to a smart traffic light that's trying to learn, on its own, how to reduce traffic jams. Okay, here's our scenario. The state is there are 10 cars waiting north-south and 5 cars waiting east-west. Our agent takes an action, keep the light green for north-south traffic. After doing that, it gets a reward of +8, let's say because traffic delay went down. We'll set our learning rate alpha to 0.5 and our discount factor gamma to 0.9. And let's just imagine that from the next state, the agent's best guess for future value is 12. So let's say before this all happened, the agent's current belief, its Q value,
for keeping the light green in this exact situation was 10. This is our starting point. This is our old knowledge. Okay, now we calculate our new target value based on what just happened. We take the immediate reward we got, which was 8, and we add the discounted future value, so 0.9 times our future guess of 12. That all adds up to 18.8. This number represents the new reality the agent just experienced. Now comes the most important part. We calculate the difference, or the error, between what the agent just saw, that 18.8, and what it originally thought the value was, which was 10. The error is 8.8. This gap, right here, is the opportunity to learn something new. And finally, we do the update. We take our old value, 10, and we nudge it using that error. But we don't use the whole error. We scale it by our learning rate of 0.5. So we're just adding half of the error, which is 4.4, to our original belief of 10. And there we have it. Our new updated Q value is now 14.4. Now notice, it didn't jump all the way to 18.8. It just moved part of the way there. After just one single experience, the agent's belief about this action has already gotten more accurate. Now imagine doing this thousands or even millions of times. It will eventually learn the absolute best way to manage traffic. So that was a pretty deep dive into the math. Let's pull back up and just quickly summarize the big ideas that you should really walk away with.
First, every reinforcement learning problem is built on the foundation of an MDP. That's our game board. Second, the Bellman equation gives us that beautiful, recursive logic for what value even means. Third, Q-learning is the practical, hands-on tool that lets an agent actually learn these values by just correcting its own mistakes. And that is the core insight here. This isn't some complex top-down plan. It's a dead simple feedback loop, repeated over and over again, that allows incredibly smart behavior to emerge from the ground up.
We just saw how a pretty simple update rule can let a machine learn a complex strategy completely from scratch. From managing huge energy grids to personalizing the videos you see online, the applications for this are just endless. So it makes you think, if this formula is all it takes, what everyday problem would you teach it to solve? Let us know what you come up with.